in the previous section, we assumed that the keys always map to different hash values. This is sometimes not true. It is possible that the mathematical function will give the same value for different key values. This is something that could normally happen in mathematical functions. As you will remember, two different values can map to the same image. So this is also possible with hash functions. So what happens in that case? This is called a collision, and how we resolve such problems is the topic of this section. So we will be discussing the following. Now, you will see the slide over and over in this chapter because we will try to keep in mind the relation of what we're discussing at the moment to the other methods. So altogether, this is called collision resolution. Once again, collision resolution means, first of all, collision is two different keys having the same hash value. This is called a collision. And collision resolution is, how do you resolve this? What kind of a solution you find when this happens? So there are basically three different approaches. You can apply separate chaining or open addressing or rehashing. We're going to discuss each one of these. In the case of open addressing, there are three different ways of doing open addressing. There is linear probing, and once you understand this, quadratic probing and double hashing are direct extensions to linear probing. Now, altogether, this part will be what we call collision resolution. So they will constitute this section and this video. The next section, and therefore the next video, is on extendable hashing. So we will not cover it in this video, but I've put it here because it is an idea that directly follows the collision resolution. So once again, the collision is happening when we map many, at least more than one key values to the same hash value. If you have a potentially huge set of strings and you try to map them to a small set of integers, why? Because we would like a limited size of array. Therefore, the possible index, if the array is small, the index set would also be small, because remember, the index is the index of the array. If array is small, that's set of integers to which we're mapping, in other words, the hash values, will be a small set. Therefore, it's likely that there will be collisions. So collision, as we said, is a second or third or fourth, whatever key, mapping to the same value, which is already used by another value, by another key. And the collision resolution is the method you employ to deal with this problem. So let's first start with separate chaining. The idea was proposed by Lund, who is an IBM engineer, back in year 1953. So it's a quite old approach. It's a very simple one. So the basic idea is, when there is a collision, when there are multiple keys that hash to the same slot, then from there create a linked list and put them in a linked list. That means all these elements, all these keys map to the same hash value, and I just place them in a linked list. It's useful for highly dynamic situations where you cannot guess how many elements there will be, how many collisions, or how often we will experience collisions. So it's for highly dynamic situations where the number of search keys cannot be predicted in advance when you're developing the system. So this shows an example. Now, here actually you have an array of 11 values. So M is 11 for us, with index ranging from 0 to 11. So actually it's a single layer. Okay, when you look at it, it looks like multiple layers, but actually it's a single layer. I have a single array of 11 elements. Note that I have not selected 10 but 11 because remember we said the value of m should be a prime value, prime number. Okay. Anyways, our input is a searching example. We don't have blanks. We just have these characters with different codes. I've not written the codes here. What you directly see is the corresponding hash values. Okay, so A is the first letter in the alphabet, so it has the value 1. E is the fifth, A is again 1. H is the eighth character, for example. G is the seventh character. I is ninth. But R is actually the 18th character. But when we take modulo 11, it becomes 7. However, note that G is also 7. The value of G was 7. The value of R is 18. But modulo 11 for both gives the value 7. So, for example, there we have a collision. Similarly, we have a collision for L, okay, which is 12. So we have such collisions. So let's see. Initially, now this is the index of our hash table, hash array, and initially it will all be empty. So you don't have these L, M, N, E, whatever. So initially it will be like I have an array like this with this index. Initially, they will all be empty, or for example, null pointers. Okay, so the first thing I see is A. I apply the hash function, which is actually, if the hash function is H, I'm applying A, so it is the value of A is 1 modulo, sorry, it just messed up here. Let me erase this, and again, modulo 11 would give me 1. Therefore, the hash value is 1. So I go to index 1, and from here, I put the value A. Then the next one is S. So I go to 8 and put S. Next is E, 5. A again. Now I come here and I see it's already occupied. There's a value here. So I will shift this A. So erase this, shift it down, and put the new A here. Well, since it's the same A, it appears to you like it's the same, but actually these are two people with different names, for example. Okay, two different students, for example. Anyway, so I have to keep 2 copies of A, therefore, because they are 2 separate students. And I have R going to 7, C going to 3, H going to 8. Now, in 8, I again have S. So what I'm going to do is I'm going to shift S down and put H in the front. Okay, so we're just inserting to the front of the linked list, in other words. And it proceeds as this way. So for example, the last value that's put to 1 would be L, so that's why you see it at the top of the linked list for 1. M and X, see here's X2 and here's M2. X comes before, so it goes down, and M comes later, so M is here, X is here. So it works this way. So these red equal sign here are just representing null. So for a linked list that's full, it's showing the end. For a linked list that's empty, the first element is null. Okay, so it's straightforward. So what's the length of the list? We have n keys. For example, here n would be the number of letters here. Just count the number of elements here, that's n. M is the size of the table. For us, m was 11. Therefore, we had index from 0 to 10. So the load factor, lambda, would be n over m, which would be also the average length of the list. Of course, if you look at this, you see that some lists are of length 4, 2, 4 again, 1, and some are 0. Because this was just an example run. Now, run this algorithm with different keys every time. Like, take keys from a book, run the algorithm, measure the result, put the average length of individual positions here. We will call them buckets, by the way. So this is bucket 0, bucket 1, 2, 3, whatever. So if you look at the bucket lengths, record them, now run it with a different input, the bucket lengths will be different. If you repeat it many times and look at their averages, you will see that if there is no bias in the input, and if you have a good hashing function, it will be almost the same for each bucket. So the average would be the number of elements divided by the number of buckets in the hash table. But as I said, this really depends on the hash function. Now, our hash function here is a very simple one. If the numbers are not biased, then we would expect in the long run to be a fair distribution of the elements to the buckets. However, if the input is somehow biased, like, for example, if you're reading numbers from the input and the person who is providing these numbers to you is always giving round values, like rather than saying 8 or 9, the guy typically says 10. Or instead of 19 or 21, he says 20. Then that means there's a bias towards numbers that are multiples of 10. So in that case, you might observe an uneven distribution. Okay, so the performance of a hashing function is actually measured by how these buckets are distributed. Are the buckets approximately of equal length? In other words, is the input distributed evenly to the buckets or not? That shows the performance of a hashing function. And it's not easy, actually, especially if the case of if the input is somehow biased. We might have, when we are searching for an element, you simply apply the same hash function and go to the bucket. And once you reach that bucket, for example, say if you were trying to find whether you have the letter, say, P in this input. So what you're going to do is you will take the ASCII code of P, apply the hash function, and you will find it's 5. You go to bucket 5, and then here you have a linked list, and you start searching in that linked list. You either find it or not. If you cannot find it, if it's an unsuccessful search, you will be realize that P is not there when you reach the end of the list. If P is there, if you find it, then you might, by chance, find it at the beginning of the list or the end of the list. Again, if there is no bias in the order the input was entered, we would expect to go, on the average, halfway down the list. Okay, again, this will hold true if you have many experiments. Individual experiments might result in good or bad results, but if you repeat the experiment many times, you will have something like half the length of the list. So this value average length of the list would be important. It defines us the worst case behavior, which is the length of the list, and the average behavior, which is half the length of the list. And of course, the best performance would be one. The first element you look is the one you were searching for. In the case of separate chaining, it's important how you choose the value of M, the size of the table. We would like to have it relatively small so that it does not use up a large area of contiguous memory, because the array itself, remember, an array is a single chunk of data structure. All bytes are consecutive, one after another. So we don't want to allocate such a huge chunk contiguous memory for an overhead like a hash table. So we would like to keep it as small as possible. But also, we know that if the value of M is small, if the table is small, then these linked lists, therefore, would be very long. If you have small value of M and large value of N, if in reverse, if the number of elements you're trying to hash is large, whereas the table size is small, then you will have long linked lists here. Because remember, the average length was N over M. If N gets larger or M gets smaller, this would be large. So we would like to have a hash table not very large, because we don't want to spare so much memory, but also not very small, because we also don't want long lists. One thing we can do is we can keep those lists ordered so that whatever I'm searching for, I can search for that faster. But this keeping that linked list sorted is yet another kind of overhead, because you have to work to keep it sorted. So the important thing there is, what is the ratio of the search operations versus insert operations? If you're mostly inserting and deleting elements to the hash, but the number of search operations, that means trying to find if that element is in the list or in the hash or not, if that's not very frequent, then it's really not worth try to keep the list sorted, because anyways you're not trying to benefit from that sorted list. So sorting itself would be an overhead that is not justified. However, if the number of search operations is very high compared to insertions and deletions, then it's worth it. So it's just like, again, our student registration system. Students are registered to the course only at the beginning of the semester, and they either do not drop the course at all, so they remain in the list or hash, or they drop once. Okay, so the number of insertions is 1 per student in every course, and the number of removals is, on the average, less than 1. Most students do not drop, some drop or withdraw. Okay, so the number of insertions and removals together would be less than 2 per student, whereas number of search operations would be much higher, because throughout the semesters we try to look at the look at the student list for different purposes, for attendance, for entering the exam scores or project scores, whatever. So the number of search operations per student is much higher compared to the number of insertions and deletions. Therefore, it would make sense to keep those linked lists in the hash buckets sorted in our case. In other cases, it may not be worth it. Another approach could be, rather than keeping the list sorted, instead of a list, you can have a tree there. So starting from every bucket, rather than having a linked list like this, you can insert here a binary tree, for example, a binary search tree. So we know that it would be log n, where n is the number of elements in here in the bucket. So log n would be better than n. It would be preferable, but in most cases, the cost of managing a tree there is not worth it unless you really do a lot of search operations. How about the advantages and disadvantages? The advantages are separate chaining is used when memory space is a concern, because the overhead it introduces is low and it's easy to implement. You just have an array and then from each position you have a linked list. The disadvantages are if the keys are unevenly distributed, which is a cause of using a not very good hash function or biased input, you might end up with very long lists, and some of the buckets will have very short lists. So the search time increases if the list is very long, and there will also be many empty spaces in the table if the keys are not evenly distributed. So we have discussed separate chaining. Let's come to open addressing. In the case of open addressing, it was invented in 1957. So the idea is store the collisions, all of them in the hash table. Don't use such linked lists to handle collisions. In this case, the table size should be much larger than the number of elements, because we're going to store these additional values somewhere in the hash table. We'll see how. Therefore, it's recommended that the table size is at least twice the number of records, typically higher. So what we do is we have this hash function again, okay? But whatever the hash function returns, on top of that, you add the result of another function which we're going to discuss and apply the modulo on top of that. That would be your overall hash function h. So this is the primary hash you're applying, the original hash value. Here, fi is what we call the collision resolution function, which is dependent on I, where I is the number of attempts. Okay, so as you have collisions, I will increase, so I will actually show the number of collisions you've encountered. So every time there's a collision, fi will return a different value, not the same value. Since this value changes here for fi, what you're adding on top of hash x, although the key is the same, you will be adding a different value for each collision. So you will end up with a different value here, which is then applied to modulo. So let's see the example. It will make it more clear. So there is a problem with deletion. We need a special flag that will show us the deleted items, which should be different than empty positions, because it's possible that you insert an element, you insert another one, which has a collision with that. So you will insert it to somewhere else. Then another one, then another one. Now, later at some point, assume that you want to delete one of these values that has collided. Okay, so you just remove it from there. Now, when you want to search again or insert a new value that has a collision there, when you come to that position which has been deleted, you should be able to understand whether that's the end of searching, or maybe it's a deleted item and I should continue. So it is required for the search operation. If we reach a deleted item, the search has to continue because actually there was something after the deleted element. There were more elements following, so you should keep on searching. Therefore, it's important to differentiate between deleted items and empty positions which were never used. So in the case of linear probing, which is a way of open addressing, remember that there were three different approaches. Linear probing was the first one. That fi function is simply the value of I. Okay, so when you want to do insertion, if there's a collision, you probe the next slot, the next position in the table. If that's unoccupied, put your item there. If that's also occupied, keep on going to the next, all the way. So you're trying to insert to where it should have been. If that position is full, try to put it in the next item to the right. If that's also full, try the other one, until you find a free position. If you reach the end of the table, loop back to the beginning of the table and start repeating it from that position. If the size of the table is larger than the size of the input, there should be open slots, so you should find it. If you have filled the whole table, then it will fail. And in that case, be careful not to go in an infinite loop, because if you end up with a full table, so if you try to insert something to a full table, your algorithm will never terminate. So you should, in other words, remember the first position you tried. If you loop around and come back to the same position, it means you had a full round and you couldn't find a position. In other words, the table was full. So no need to search again, because you won't find anything. So you should terminate there, not to go into an infinite loop. But also it shows that your table was full, which should not have happened. You have another problem. We will deal with that later. When you're doing searching, you again apply the hash function, get the hash value, go to that address, and check if that's what you're searching for. If it matches, then that's a successful search. So return the value and terminate. If it's an empty position, that means, by the way, if it doesn't match, before going into that, if it doesn't match, you look at the other one, because there could have been a collision, so it could have been placed into another position. So keep on repeating this. So that's the third approach here. But if you end up with an empty position, that means you've hit the end of search and you couldn't find it. So what you're searching for is not in the hash table. And as I said, if you reach the end of the table, both in search and insert, you loop back to the beginning. So you have a round. Let's look at an example. Again, the input, here's again a searching example. Here we have the hashes. Here our m value is, it's not written here, but our m value is 19. How did I understand that? Well, I look at the index. The index goes from 0 to 18, so m is 19 therefore. We're applying, in other words, modulo 19. Since we're applying modulo 19 for some values like n, m, p, l, we're not using modulo 10 anymore. 11, sorry. Earlier it was 11. But we're applying modulo 19, which is, pay attention, again, a prime number. It's possible to have such large values. Anyways, let's try to insert them. We just insert them one by one. So we, for example, we see A here. So we put A in index 1. Then we see S, that's 0. So we put S in index 0. Then we see E, we put it in 5. And we see A once again here, whose index is 1. But when I go to 1, I observe that it's occupied. So actually, all I do is I search for the next position. So this was full. So there's a collision here. Actually, I don't do anything, but I'm marking it with a start here just for you to see it. Actually, I don't do anything on the array. In reality, you don't do anything, just to show you that there was a collision, to make it better, easier for you to follow the example. We mark the collision here, and we search for the next position, which is 2, and it happens to be empty. So we actually write A here. But I will show it down here, not here. Just for you to follow that it was placed not in the first round, but it was placed in the second round. Just for you to understand it. Actually, in reality, this second A was in fact written here, and there was actually, it was like, we don't have such a mark, and also we don't have this. Reality is like this. We don't have these. There's E here. X, G, H, I, N, L, M, E, P, R is here. Anything else I didn't show? The reality is this. You're just keeping this array, that's all. Like this, okay? However, for you to easily follow that, we have used these. So let me just erase all these marks so that you can follow it easier, so that you see in which round it was placed. So A was placed here in the first round in number 1, but the A in slot 2 was placed in the second round because the first round had a collision here. For the case of C, the value of C was 3 and that position was available, so we have placed C here. But then when we after C we have H, so that's placed in H is supposed to be placed in 8. We have I placed in 9. Then N is placed in 14. G is placed in 7. E is supposed to be placed in 5. When we go there, we see that it's already occupied. So we put it in 6. Okay. X is again 5. Note that both E and X have the same value. So you try to put X here, but there's E in 5. So we cannot put it there. We try the next position. There's E in 6, so we cannot put it there. We try 7, but G is there. 8, H is there. 9, I is there. And finally, 10 is available, so we put X in 10. How many collisions did I have for X? 1, 2, 3, 4, 5 collisions. Only in the 6th attempt, I was able to place it. How did it work? Actually, H of really the element itself is X. For X, what I do is hash of X plus F initially equal to 0 modulo 19. So hash of X is, I know it's 5. F of 0 actually is equal to I here. This was I, so it's initially 0. 5 plus 0 is 5. Modulo 19 is 5. That's why I tried 5. I had the collision here. So next, this doesn't change. Hash of X is always 5. So next, this 0 will become 1. Therefore, this will become 1. So 5 plus 1, 6. Modulo 19 is 6. Try 6. That's also occupied with another occurrence of E, which was actually the second occurrence of E here. The first one was here. So again a collision. So increment I becomes 2. So this becomes 2. 5 plus 2, 7. 7 modulo 19. There I have G becomes 3. So it's 8 modulo 19. It works this way. So it is 0, 1, 2, 3, 4. Finally, when I is equal to 5, we have 5 plus 5, 10. Modulo 19 is 10. We go to 10, index 10, and we see it's available and we put X there. That's how it works. So that's basically what linear probing does as a mechanism for open addressing. So the disadvantages we have just encountered in the case of X what we call primary clustering. Again, primary clustering occurs when we have these elements all placed here from E to 9. All of them, remember, were full. Once again, let me write that with these values. So here we had a cluster, a sequence of positions that were all full, one after another. This is called primary clustering. Because of this clustering, I had a sequence of consecutive collisions, which is not nice. Okay, so this linear probing suffers from what we call primary clustering. Large clusters tend to build up, especially when M is large. We will have large clusters. So the expected number of probes for insertions and successful searches, we'll not go into the proof of this, is 1 over 2 times 1 plus 1 over 1 minus lambda squared, where lambda is, remember, number of elements, and divided by M, which is the size of the table. In other words, it was, remember, the load factor. So lambda is the load factor. 1 minus lambda is not the load, but the ratio of the available positions. Load factor is the ratio of full buckets. 1 minus lambda is the ratio of free buckets. That ratio squared, and then take the reciprocal and add it to 1 and take its half. That would be the average or expected number of insertions and unsuccessful searches. For successful searches, it would be 1/2 times 1 plus 1 over 1 minus lambda. As I said, we're not going into the proof of that, but this is what you would observe in the long run. Now, remember the problem. We said the problem was primary clustering, and that's because my Fi function is simply I. So once I have a collision, I try the next neighbor, next neighbor, next neighbor, next neighbor. So I'm creating the primary clustering by hand. So what if I slightly change this Fi function so that rather than going 1, 2, 3, 4, 5, I start jumping. So 1 makes sense. If there is a collision, try your next neighbor, 1. For the next one, rather than trying 2, try square 4. Then 9. So every time there's a collision, you're having larger jumps so that you avoid these clusters. If there is a cluster, try to jump away from the cluster. Okay, so instead of f of I being equal to I, now in the case of quadratic probing, as the name implies, we have a quadratic function, which is I square. So hopefully we will be able to skip over the regions that form the clusters. This is explaining what I already did. So first try its correct position. If not, try the next. Then jump 4 positions, 9 positions, 16 positions, 25 positions. Work this way. Then there is double hashing, which is just an extension on this. Rather than applying I square, you have another hash function, a different hash function. So we call that hash2 of x. Now, if that hash function itself is equal to I, it would be I times I, which would be quadratic hashing. If hash2 function of x is 1, then fi would be equal to I, which would be linear probing. Instead, what we do in here is in place of hash2 of x, we write r minus whatever the key is, that modulo not m but r. Here r is a prime value which is smaller than m. Okay, so you again pick a prime value, but it should be less than the size of the table. And one thing you should pay attention to is hash2 of x should never evaluate to 0, because if that happens, you would have fi equal to 0, which would be the current hash value. And once you get there, you will just get stuck there. Therefore, it should be an r value which never becomes 0. Well, does this become 0 ever? Now let's see. Since this is something modulo r, the result of this parentheses would be something between 0 and r minus 1. If it's 0, it would be r. The other way around, if it's the largest value, which is r minus 1, r subtracted r minus 1 would give you 1. So the smallest possible value of hash2 of x would be 1. And this provides us, pay attention, different ways of jumping around. So we will hopefully not have clustering. So we have discussed separate chaining, where when there was a collision, we created a linked list. Open addressing, where on top of hash function, we added some fi. Then we took the modulo, where fi was either I or I square, or based on some other hash function, which was r minus x modulo r. And after we do this to resolve the collisions, there is still the possibility that my hash table is very close to full. Therefore, a full hash table will typically have, or not completely full, but a hash table that's close to full is very likely to have frequent collisions. And as I have collisions, we have seen that I need to do more and more operations, which means I'm a little bit losing the benefit provided by hashing. So I would like to keep my hash table large enough that I don't have frequent collisions. So we know the size of the table should be larger than n, but how large? I would like to achieve a lambda or load factor that is in general approximately around 0.5, which means I would like to keep my table half full most of the time. That means I'm keeping the table also half empty. But the cost incurred by having a half empty hash table is outweighed by the benefits of hashing, which allows me fast access to the elements. So the rule of thumb is to have something around 0.5. Of course, it will not be exactly 0.5. And when it hits around 0.75%, which means my hash table is 75% full, then I have not hit the full table yet, but it is a good idea now to do rehashing so that I improve the performance again. Because if I reach 70% fullness in my table, it means I'm going towards the trouble. So I would like to resolve it as soon as possible before I hit the trouble. So rehashing is quite simple actually. Why did I have rehashing? Because lambda has exceeded 75%. You cannot change the number of elements. It's not under your control. The user is entering the input. In that case, what you can do is you can change the table size, which means increase the table size. Since I'm trying to lower lambda towards 0.5, if I cannot control the numerator, I will increase the denominator so that the ratio becomes smaller. Okay, so increasing the denominator, increasing m, means creating a larger page table. Larger hash table. So what you do in that case is you create another hash table which is larger, and you start moving the elements one by one from this hash table to the new hash table. Once you do that, you can discard that old, smaller hash table. But while you're doing this, all operation stops, because at the moment the value of m has changed. You should not be inserting anything to the hash table before you have moved everything from the old hash table to the new hash table. So that means when this happens, when your program needs rehashing, suddenly you will realize that your program is not responding, and in the background, typically, for example, you would be hearing the hard disk working, because actually there it is doing rehashing, moving things around so that you end up with a larger hash. Of course, if you're doing it on the disk. If you're doing it in the memory, then it's faster. So we're building a larger table and then rehashing everything. Why do we say rehash? Because the value of m has changed, which means, remember, we applied for the hash function modulo m. So m has increased. Therefore, I have to recalculate the hash values, because the hash values of the elements will change when that modulo m changes. It's an expensive operation because you have to go over all elements one by one. Therefore, it has a cost of On. But once it's done, this new hash table, the larger hash table, has a better performance. Okay.